Okay, let's get started. Bartram, Blair. Let's see who is here from Zoom. Donnelly is here. Elwell, Levingood, Miller, Sheffield, Sullivan, Tillis. All right. So let's continue our discussion of chapter 3. And the last time we're here, we're just about to do these questions. And these questions are basically dealing with molarity. So let me start with the first one. In fact, let me copy and paste this onto a Word document so I'll have space to show you how to do this. Okay, so here's a question. What's the molarity of a solution in which it's 333 grams of potassium hydrogen carbonate is dissolved in enough water to make a 10.0 liters. Something is wrong with my eyes today. 10.0 liters of solution. Okay, any ideas? How do we do this? The question is asking for the molarity, right? Question gave you the mass of the potassium hydrogen carbonate, and it gives you the volume in liters. So that's basically what I circled are the three essential parts of this question. What's your name again? So. All right, so any ideas? What's the formula for molarity? Molarity is equal to what? Let's start off with that. Moles of solute divided by liters of solution. Okay, so we're given one part of this equation already. We're given the liters of solution. That's the 10 liters here. So the real issue is, how do we determine the moles of the solute? Okay, so how do we do that? We're given 333 grams of potassium hydrogen carbonate. So how would we convert that to moles? Calculator. What would be up here as the numerator, and what would be down here as a denominator? You have to find the molar mass of potassium hydrogen carbonate. So, let's see from here. So potassium would be 39 point, let's say 1.10. So 39.10 plus hydrogen, which is 1.008, plus carbon, which is 12.01, plus 3 oxygens, that's 3 times 16, 48. So what I got, and you can tell me if you agree with me, I got the molar mass be equal to 100.12. So let me put 100.12 grams of potassium hydrogen carbonate. And here I'm going to have 1 mole of KHCO3, all right? So this will cancel out with this. So basically, the only thing that's left for us to do now is divide the result of that by 10.0 liters. So let's see what that gives. 333 divided by 100.12 divided by 10. So according to my calculations, this works out to be equal to, rounded off to 3 sig figs, 0.332 M. All right. Any questions about this? Any questions? Okay, so that's a relatively simple example. I think the others are a bit more complicated. Is it okay for me to, is it okay for me to erase this? Okay, so let me get rid of this here. And let me go back to the PowerPoint. And let me copy this question. And then go back to Word. Okay, so here's a question, actually a two-part question. It says we want to prepare a 6.68 molar solution of sodium hydroxide. So the first question is asking how many moles of sodium hydroxide are required to prepare 0.500 liters of 6.68 M sodium hydroxide. So any ideas about this one? Actually, this one is kind of easy, just as easy as the one that we just did. So the question is asking for the moles. They gave you the volume in liters and they gave you the molarity, right? So how would you go about solving this problem? Well, remember the formula for molarity, which we used a while ago. Moles of solute divided by liters of solution, right? So what the question is asking for is this part right here. So how would you rearrange this equation to solve for the moles of solute? Exactly. So the moles of the solute would be equal to the liters times the molarity. All right. So they gave you the volume in liters, which is 0.500 liters, multiplied by the molarity, which is 6.68 M, which is the same thing as moles per liter. And just by looking at this, I can say that the answer is 3.34 moles. And that's how that is done. All right. Any questions about this? Yeah, there shouldn't be any. This is too easy. All right. For B, it's asking how many liters. So you're using the same equation here, but this time the question is asking for the liters of solution. All right. So let me get rid of some of this stuff here. We'll get rid of this here. Okay, so what would you do in this case, in the case of D? They asked for the liters, they gave you the molarity, and they gave you the mass of sodium hydroxide in kilograms. So how would you rearrange this equation here to get liters of solution? Liters of solution is equal to what? You sure about that? Anybody else? How would you rearrange this equation? Or would you rearrange this equation to get an equation where you have liters of solution equals to something on the right side of that equal sign? Should be simple algebra, folks. multiply. I'm sorry? Nope, nope, nope. Come on, guys. You should know how to do this. I'm sorry? Exactly. Moles of solute. Man, I need to talk to your algebra instructors, see what is happening in those classes. Divided by molarity. Okay, very good. So they gave us a molarity already. That's a 6.68, but we do not have the moles of solute. But what they have given us is the mass of the solute in kilograms. So my question to you is, how would you convert this mass, 2.35 kilograms of sodium hydroxide to moles? What's the first conversion factor? There's more than one conversion factor involved. So what would be the first conversion factor you would employ? That's true, but that's not right here, right now. That's later on, but that is indeed what you're going to use in the next conversion factor. But for this conversion factor, what do you need to do? Exactly. So 1 kilogram down here, 1,000 grams above. All right, so that the kilogram units will cancel out. And then, as you suggested, the molar mass comes in, right? So the molar mass of sodium hydroxide is 22.99 plus oxygen, which is 16, plus hydrogen, which is 1.008. So that would be 40.00 grams per mole. And this is how you arrange it, because you want the gram units cancel out. So you're left with moles at the end of this process. And then you divide all of that by the molarity, which is given as 6.68 moles per liter. And then you're going to see that the mole units cancel out. So the final units would be in liters. So now we have to do the number crunching. 2.35 times 1,000 divided by 40 divided by 6.68. So according to my calculations, rounded off to 3 sig figs, the answer becomes 8.79 liters. And that would be the answer. All right. Any questions about this one? Any questions? No questions? Okay, so let me see here. So one more question coming up. Now this one, I'm going to just copy and paste again. And let me erase the writing. Oops. Okay, so the question here says, the label of a stock bottle of aqueous ammonia indicates that the solution is 28.0% by mass and has a density of 0.898 grams per mil. So the question is asking for us to calculate the molarity of the solution. So let's remind ourselves again of what the molarity by definition is. Molarity is equal to the moles of solute divided by liters of solution. Now in this case here, we're not given the moles of solute and we're not given directly the liters of solution, but we can still use this equation to some degree to help us to calculate this. Because another way of looking at molarity is basically the moles of solute in 1 liter, right? So what I can do is start off with 1 liter of solution, right? So let's assume that we have exactly 1 liter of solution, all right? The first thing I can do with this is find out the mass of the solution. Why? Because I'm assuming 1 liter of solution and we have the density of the solution right here, right? So in order for us to go from liters to mass, what I would do first is convert from 1 liter of solution to milliliters. So Of course, we know that 1 liter is the same thing as 1,000 milliliters of solution. So that this unit cancels with that unit. And then the next step would be a conversion factor which represents a density. And the way I'll do that is that I'm going to put 0.898 grams of the solution divided by 1 milliliter of the solution. All right. So this would go with that. All right. So what I've calculated up to this point would be the mass of the solution. Now, another important information given is that this solution is 28.0% by mass ammonia, right? So basically, since we have at this stage determined the mass of the solution, we can calculate the mass of ammonia in a solution because according to the information provided, 28% of it by mass is ammonia. And the way I would represent that here is that I would have up here as a numerator 28.0 grams of NH3, and down here I would have 100 grams of solution, right? Because that's what the information says. 20% of the solution would be ammonia. So in terms of units cancellation, this will go with that. So what we have calculated successfully up to this point would be the mass of the solution or the mass of the ammonia in 1 liter of solution. So the only other thing left for us to do in the next conversion factor is to convert the mass in grams of ammonia to moles. And again, we have to do the molar mass calculation. So nitrogen is 14.01 plus 3 times 1.008. So according to my calculation, the molar mass of ammonia is 17.03 grams of NH3 for every 1 mole of NH3. And that's basically the setup. So now let's do the number crunching. So 1,000 times 0.898 times 28 divided by 100 divided by 17.03. And according to my calculations, this works out to be equal to 14.8 moles. All right. So basically, for 1 liter of solution, the moles of NH3, let me write NH3 here, would be 14.8 moles. So therefore, we can say that the molarity of the solution, is equal to 14.8 M. And that's basically how that is done. All right. Any questions about this one? Any questions? Any questions? No questions? Okay, so let me hold on 1 minute. Okay, so let me go back to the PowerPoint and we're going to continue our journey in chapter 3. The next thing we're going to talk about is dilutions. And unfortunately, for those of you enrolled in my lab, we touched on this topic or covered this topic before we covered it in the lecture. But it's a pretty simple topic. And in any case, this is something that, again, you should have met in your introductory chemistry, high school chemistry. But basically, dilution is a very important process, very simple process, and is employed in labs all over, not only in chemistry labs, but basically any lab situation where chemicals are used, right? Because very often what you'll find is that you might be doing an experiment or you plan to do an experiment where a particular solution of a particular concentration is required, but in your stockroom, you have a more concentrated solution at hand. And therefore, what you'd have to do is basically dilute the solution that you have to the level that you want so that you can do whatever you need to do with it, right? So as stated here, dilution is basically the process of adding more solvent to the solution, and therefore, as a result, the solution becomes less concentrated. The key thing underlying the whole dilution process, especially when it comes to the calculation, is that when you add a solvent to the solution, while you're increasing the volume of the solution, you are not affecting the amount of solute in the solution, right? The amount of solute changes, well, it doesn't change, but the volume changes. And therefore, because the volume changes, the concentration will decrease, right? So therefore, there's an inverse relationship that exists between the concentration and the volume of a solution, assuming that the amount of solute remains the same. And as stated here, which is what I said earlier, it is very common to prepare a concentrated stock solution of a solute and then dilute it to other concentrations as needed, right? So, and you know, this happens in almost every lab. It doesn't matter the level of sophistication of the research or work that is being done. In labs like ours, educational labs like ours, we do it almost every week, where we basically have to dilute solutions to the level that we need to in order to make a solution of the required concentration. Okay, so as I said before, this is what happens. You're adding solvent to the solution, and example here is a solution of iodine, right? So the initial concentration of the solution is 0.050 m. The initial moles is given here, 0.0050, and the initial volume is 0.10 liters, right? And this is just a picture representing what happens at the microscopic level in terms of the relative amounts of solute molecules to solvent molecules. When you add your water to it, your solvent to it, then what happens? The volume increases. So in this particular example, the volume increases from 0.10 liter to 0.50 liter, but you'll notice that the moles of solute doesn't change. So the result of that is that the concentration decreases from 0.050 m in the case of over here to 0.010 m, all right? So basically, as you increase the volume, the concentration decreases, and that relationship is an inverse relationship, all right? So in terms of the actual quantitative calculations involved, it's pretty easy, right? Because the moles of solute does not change on dilution, that means that the moles of solute will be equal to the molarity times the volume, and that product does not change. So therefore, as a result, we can say that the concentration of the more concentrated solution times the volume of that same solution would be equal to the concentration of the dilute solution times the volume of that dilute solution. And this is, you know, in most textbooks, they refer to this as the dilution equation, which, as I said before, we employ whenever we want to dilute solutions to a specific concentration. How do we do this in practice? Well, as I said before, in the lab that I teach, we have done this before, but this is just another example that I'm showing here on the screen. So in this particular case, the question says how many milliliters of a 0.20 m copper 2 sulfate solution, stock solution, is needed to prepare 0.25 of a 0.40 m copper 2 sulfate solution. So whenever you're doing questions like this, the dilution equation is what you're going to use, right? Let me just write it here. Now, I prefer to write it like this. It's the same thing. C1 V1 is equal to C2 V2, right? So C1 and V1 would be the initial concentration and volume of the more concentrated solution, and C2 and V2 would be the concentration and volume of the more dilute solution, right? So whenever you're given a question like this, it's important for you to examine the question and identify what is C1, what is C2, and what the question is asking for, right? So in this particular case, it's asking how many milliliters. So the first thing I would say is that what the question here is asking for is V1, right? Of a 2.00 m copper 2 sulfate solution. So this would be C1, right? And then this volume here would be V2, and this here would be C2, all right? So you need to identify the terms first in the question. And then now, since the question is asking for V1, I would rearrange this equation here to get V1 is equal to C2 V2 over C1. And then I'll plug the numbers in. So C2 is 0.400 m times V2, which is 0.250 liters, and then divide that by C1, which is 2.00 m, all right? And then you do your calculation. So 0.4 times 0.25, and then we divide that by 2, And the answer here would be 0.0500 liters, all right? And that's basically how that is done, all right? Now, before I move on to the actual practical steps involved, let me just say that whenever you're using this equation here, let me go back to this equation here. Whenever you're using this equation here, it does not matter what the units of the concentrations or volumes are, right? However, whatever the concentration units that you use for C1, the concentration units for C2 must be the same. And the same is true for the volume, right? The units for V1 must be the same as the units for V2, right? So therefore, it doesn't matter. The volume units could be in milliliters, liters, gallons. It doesn't matter, right? As long as they're the same on both sides. And the same is true for the concentration, because there are different ways, of course, of expressing the concentration. We're just dealing with molarity right now, but you can have concentration expressed in percentages, for example, percent by mass or percent by volume. It doesn't matter as long as the concentration units are the same. And the reason why I make mention of that is because you could be given a question where V1 is given in milliliters and V2 is given in liters, right? So if you encounter a situation like that, then obviously what you would do is convert either the milliliter value to liters or vice versa, right? So that is something for you to look out for. So let's look at the practical aspects. As I said before, students in my lab would be familiar with this by now. So basically, we have some important glassware that we use in this type of exercise. We have this, which is called a pipette, right? The pipette is a special piece of glassware. They come in different sizes, and they're designed to measure accurately a specific volume, right? So you can have a 10 ml pipette. I think the smallest one I've seen is a 5 ml pipette. And the largest one I've seen, I think, is actually the one that we see here, which is a 50 ml. I don't think I've seen one larger than that, all right? And I don't think you'll be able to see it from the picture here, but all pipettes of this type has a mark which is etched on the stem somewhere about here of the pipette, right? That mark represents the actual volume you're trying to measure, right? Accurately, right? And when I say accurately, I mean up to 2 decimal places. So we're talking about 50.00 mils, all right? So that's basically how this is designed. And basically what you do, it's not fully shown here. You would attach what is called a pipette filler, and then you turn the wheel and it sucks up the liquid as you dip the tip of the pipette into your solution right here. And you basically pull up, it sucks up the liquid up into the pipette, and then you pull it up until the meniscus gets at that mark, right? And then you know that you have 50 mils of your solution in the pipette. And then you just simply take that to another important piece of glassware that we were introduced during the Chem 1 lab. That's called a volumetric flask. That also is a very accurate piece of glassware, come in different sizes. The one that we used in the lab last week was what was it? 100 mils, right? 100 mil volumetric flask. This one is a 500 mil volumetric flask. No, I'm sorry. What am I saying? 250 mils or 0.250 liters volumetric flask, right? So there's also another mark. And again, I don't think it's shown here clearly, but there's a mark that is etched on the stem of that flask, again, reflecting the volume of the liquid that's in it if the meniscus gets up to that point. So basically in practice, what we do is take the 50 mils of the more concentrated solution, transfer it to the flask, right? And after that, we add water to it. And we, in the lab, what we did is add water up to about a third full. We stopper it, we shake it up, and then we add water more slowly until the meniscus gets up to that mark. And then we shake it up again to make sure that the solution is homogeneous. And that's it. And that's how we prepare accurately a solution by dilution, all right? Okay, so much for that. So let's talk about chemical reactions where these reactions are done in aqueous solutions. And basically what you're going to see now is that we're going to apply what we learned earlier with respect to stoichiometry and also what we just learned with respect to solutions and concentrations and so on. So as stated here, molarity provides an additional tool. in stoichiometric calculations based on chemical equations. And again, let me stress, again, I don't think I need to do so, but just in case you have forgotten, whenever you're doing any stoichiometric type problems, you must start off with a balanced equation, right? You cannot do any stoichiometric problem unless you have a balanced equation to work with. The second point being made here is that molarity provide factors for converting between moles of solute and liters of solution of either reactant or product, all right? I think we might have an example or two to look at in order to see this demonstrated, all right? So this is basically I would call this a flow chart or a diagram, which basically shows you how we go about, how we used to go about stoichiometric type problems based on what we learned earlier. You may be given a mass of one substance, you convert it to moles, and then based on the mole fraction or the mole ratio between one substance and another, based of course on the stoichiometry of the equation, you can calculate the moles of the other substance, and then you multiply that by the molar mass, and that gives you the mass of the second substance that you're concerned with, right? Now, if you're talking about a solution problem which involves aqueous solution, then maybe what you need based on information is to convert from the molarity to moles if you're given the volume. So as stated here, if substance A is a solution of known concentration, then basically we can calculate the moles by multiplying the molarity by the volume in liters. And then that will start your problem solving at this point right here, right? So, and I think we're going to see an example where this is done. If B is in a solution, then again, depends on how the question is worded, then you can go from moles of substance B to either molarity or volume based on whether or not you're given volume or molarity respectively, all right? So that's basically an additional thing to consider in addition to what we have been doing before when it comes to solutions involving reactions, aqueous solutions, all right? Okay, so I thought I had an example, but I guess not. Let me see here. Let me bring up let me bring up the assignment number 3. I want to see there's a solution stoichiometric type problem. If not, I'll just search for one online and then we can do it together. Okay, there's none here. All right. So what I'm going to do is look for a solution stoichiometry worksheet difficult problems. Let's see. Where shall I? Let me see what this offers. Oh, that's stoichiometry. I'm looking for solution stoichiometry. Back up here. Solution stoichiometry. That's what I'm looking for. Let me see what is on top here. Okay, they provide the answers here. This is not too much fun. Okay, let me copy and paste this one. Let me go Word. Let me do this. And let me get rid of the writings here. Okay, so this is a question. 60 mils of a 0.322 m potassium iodide, I guess, solution are combined with a 20.0 mils of a 0.53 m lead-2 nitrate, again, I guess, solution. So the question is asking how many grams of lead-2 iodide will precipitate, all right? So as I just said a while ago, the first thing we need to do is write down a balanced equation for this reaction. So what would be, let's start off with the reactants and products. What would be the reactants based on information provided? Okay, potassium iodide, which is Ki, plus, what's the formula for lead 2 nitrate? Anybody can tell me? Lead 2 nitrate. PB, not quite. Not quite. NO3, and you're missing something. Lead 2 nitrate. Exactly. Very good. Okay, so those are the reactants. So what do you think the products are? And I'm looking forward to these two guys answering because we covered types of reactions, and this is one particular type of reaction that we covered in intro. Don't know about the rest of it. I don't know what you guys did in your course, but I know these two should know. Hmm? There you go. See, she's putting you guys to shame. Okay. You're getting there. So you're on the right track. So if they switch, what would you say the products are? By the way, who did you do intro here? Oh, Caps? Okay, all right. Yeah, so what would be the result of switching? Well, if this switches with this, what will be the result? Nope, it's switching. Because remember, potassium and lead are both cations. So the cations will switch, right? Lead iodide, what will be the formula for? Actually, it will be lead 2 iodide. So what will be the formula for lead 2 iodide? PbI2, very good. Her memory is coming back. All right. And then what will be the other product as a result of the switch? KNO3, very good. All right. You're just waking up. All right, so then we have to balance it, right? So how do we go about balancing this? Oh, and by the way, the term I think you were looking for is either double displacement or double replacement reaction, right? In some textbooks they call it double displacement or double replacement. Yeah. Okay, so balancing this, how do we balance this? Okay, put a 2 here. Exactly. Okay, so that's what we have to start off with first. We have to start off with a balance equation. All right, so let me erase this here, this here, this here. Okay, so the next step would be looking at the numbers, right? So the question says that we have 60.0 mils of a 0.322 M solution of potassium iodide, and that is combined with 20.0 mils of a 0.530 M solution of lead nitrate. So this is what I would do. I would start off by finding out the moles of each of them. So let me start off with the moles of potassium iodide. That would be equal to the 60.0 mils, and then I will convert that to liters, 1 liter over 1,000 mils, and then I will multiply that by the molarity, which is 0.322 moles over 1 liter. All right. So let me do this now, calculation. 60 divided by 1,000 times 0.322. And according to my calculations, this works out to be equal to 0.0193 moles, right? And then I'll do a similar calculation for the lead 2 nitrate, so moles of PbNO32. That would be equal to 20.0 mils times 1 liter over 1,000 mils. And then I'll multiply that by its molarity, which is 0.53 moles over 1 liter. And then let me do that number crunching. So that's 20 divided by 1,000. And then I multiply by 0.530. And according to my calculations, this would be equal to 0.0106 moles. All right. So now that we have the moles of the reactant, now remember the aim of the question is what? The grams of lead 2 chloride, right? Which is lead 2 iodide, I'm sorry, which is this right here. All right. We want to find the mass of this. All right. So let me see if you remember what we discussed in this chapter. If we have earlier in this chapter, in fact, I think we discussed this last class. So we have the moles of 2 reactants, right? And the question is asking for how many grams of one product that would be produced. So my question to you is, what do we need to find out in order for us to figure out how much product you expect to get? If you're given 2 reactants in a reaction and you're given their amounts, right? There's something that we need to find out in order to figure out how much product we expect to get. What is that important? There's an important word I'm looking for, not word, but term I'm looking for. The limiting reactant. All right, man, she's waking up now. Okay, the limiting reactant. So since you said it, how would we find the limiting reactant in this case? Don't freeze now. How would you find a limiting reactant? Or anybody? How would you find a limiting reactant? I'm sorry? Nope. Big mistake. Can't assume that, because you have to take into account not only the numbers themselves in this case, but the stoichiometry of the equation. So how would you find the limiting reactant? Okay. Partially right. And I know what you're thinking of, because I think the examples that we looked at earlier, you were given the grams to start off with. But in this case, we're starting from the moles. If we're given the grams, then you'd have to convert to moles. But that's not necessary because we're given the moles of the reactant. So now that you have the moles of reactant, then what would you do? What would be the next step? Mole ratio. Okay, so let's start off with the potassium iodide. 0.0193 moles of Ki, right? And you want to find, remember, ultimately you want to find the mass of the lead 2 iodide, right? So my question to you is, what would be the mole ratio that you're going to use to convert from moles of potassium iodide to moles of lead 2 iodide? Okay, so what goes where? What goes up top and what goes below? 2 moles of potassium iodide at the bottom and 1 mole of PbI2 above, right? So let's do that calculation. So that's 0.0193 divided by 2, right? So according to my calculation, this works out to be equal to 9.65 times 10 to the minus 3 moles of PbI2. All right. Okay. Need to scroll down here, get some more space. Okay, then what? Okay, the 0.0106 moles of PbNO3. All right, 2. Okay, so again, what would be the conversion factor in this case? What would go up top and what would go below? Right, because it's a 1-to-1 mole ratio between the lead-2 nitrate and the lead-2 iodide. So I'm going to put 1 mole of PbNO3 below, NO3 below, and 1 mole of PbI2 above. All right. Okay, and that will give 0.0106 moles of PbI2. Okay, and then what? Well, the smaller value here would come from the limiting reactant here. All right, which I think is what he was alluding to, but he did not take into account what we had to go through before. So this here, the potassium iodide, is the limiting reactant, right? So basically, to answer the question now, remember the question is asking for the mass in grams of lead-2 iodide. So what would be, how would you go about doing that? We're given the moles. So what's the next step? Exactly. So you're going to have 1 mole of PbI2 here and the molar mass. Okay, so lead has a molar mass of, where is it? Okay, so molar mass of lead is 30.97 plus 2 times the molar mass of iodine, which is 126.9. So according to my calculation, it's 284.8. So that number goes up here to 84.8 grams of PbI2. And then whatever this gives, that would be what the question is asking for. So I'm going to multiply 284.8 times 9.65 times 10 to the minus 3. So the answer I got, and please again, correct me if I'm wrong, because I can make mistakes. But the answer I got here is 2.75 grams of PbI2. All right, so that would be, this here would be the question being answered. All right. Okay, so that's an example of a typical, what do you call it now? Solution stoichiometry type problem. All right. So that's basically the end of this chapter. So based on what we have covered, see if I can, hold on. Based on what we have covered so far, you should be able to answer all these questions here. So I'm going to leave these questions for you to do. Where did we stop in doing this? I think we stopped here, right? Or did I leave this for you guys to do? Or did we stop at 11? Oh, we did number 12. Okay. So now you should be able to do the other questions. Let me just check something here. Yeah, you should be able to do that. And these are basically solution problems. All right, so I'll leave these for you guys to do. If you have any questions, of course, please feel free to contact me. I have office hours later. I have office hours tomorrow. So you can contact me during those times so that I'll be able to help you. So let me get back to well, we have to move on now to chapter 4. So let me see if I can download that PDF. I mean that PowerPoint. And in chapter 4, the focus would be on reactions in aqueous solutions. Okay, where is this thing now? What is going on? Oh, I'm clicking on the wrong stuff. I should be down here. So as I said before, the focus of this chapter is basically the different types of reactions that can take place in an aqueous solution. Now, a lot of these solutions involve ions, right? We'll be talking a lot about reactions that certain ions will undergo. So it's very important for us to have an appreciation for the type of electrical properties displayed by ions in aqueous solutions, right? So of course, you know that there are two types of charges that you'll be concerned with in these kinds of solutions. You have positive and negative charges. And this diagram here basically shows you the nature of these charges in terms of the type of forces that exist between them when they're brought together in close proximity. So if you have two particles that have no charges, then there won't be any attractive or repulsive forces between them. If there's any force between them, it would be gravitational. And depending on the size of the particles, you can ignore that for the most part. If the charges are opposite, then there'll be attraction between them. And if they're the same, as you can see here and here, you're going to have repulsive forces. So that's basically how these charges behave, right? And it's kind of similar to what you'd observe with bar magnets. If you play with bar magnets, you'll know that if you have a bar magnet, one end is negative, not negative, but one end is the north pole of the magnet, the other one is the south pole. And if you have another magnet similarly shaped or whatever, if you try to bring two like poles together, there'll be a repulsive force, all right? If you bring opposite poles together, then they'll be attracted, all right? So what we'll be looking at here is the type of electrical properties displayed by ions in an aqueous solution. And one thing I want to say here, firstly, is that one important property that these ions have is that in an aqueous solution or in a molten state, these ions can allow the liquid to conduct electricity, all right? And I don't know how many of you have done physics, right? But in physics, I remember I minored in physics in undergrad, so I remember some aspects of it, not everything. But one thing I do remember is that when it comes to currents, electric currents, they are as a result of mobile charges, right? Charged particles moving through a particular medium. Now, in the case of metals, you know, like copper, silver, etc., the charges in those cases would be electrons. And that's because in the case of metals, you have what are known as free electrons able to move, right? So if you apply, let's say you have a wire and you apply what is called a potential difference, basically the electrons will move under that influence and therefore you have an electric current. Now, in the case of a solution or in the case of a molten ionic compound, the charges that are mobile in those situations will be ions, positive and negative ions, and they can also conduct electricity. So that's what's being demonstrated here, right? You have, let's say this is your solution, and you have the ions, you know, very mobile, they can move around. You have the negative ions, you have the positive ions, and you stick two electrodes. Electrodes are basically usually metals, but you can also have graphite being another non-metal substance that can be used for this purpose. They basically allow an electric current to pass through it as well. If you dip those electrodes into your solution, and those electrodes are connected by wires to an electricity source, which could be a series of cells, then basically what will result is that you're going to have a current flowing through the entire system. Now, the current that is flowing through the external wires would be the electrons, right? While the current that flows through the solution right here would be as a result of the ions being moving under the influence of these two electrodes. And there are special names given to these electrodes right here. One is called the anode because it is connected to the positive part of the electricity source. And the other one is called the cathode because it is connected to the negative part of the electricity source, right? So basically what you'll have is that the negative ions will be attracted to the anode, which is positively charged, and the positive ions will be attracted to the cathode, which would be negatively charged. And that's where we get the terms anions and cations from, right? Anions are attracted to the anodes, cations are attracted to the cathodes, right? Anions are negatively charged and cations are positively charged. Okay, so that's basically one important property of solutions that contains ions. Okay, and let me see, let me see, I think, oh, right, so I covered this already, all right? So let me talk about now another term, in fact, some terms that you're going to need to understand in this chapter. Now, there are some solutions that can conduct electricity, while there are other solutions that will not, and it's all based on the type of solutes that are present. As we saw earlier, if the solute is ionic, then electricity can pass through those solutions. But if you have a solution where the solute is not ionic, such as this example right here, methanol, it dissolves in water, but does not produce ions, right? So basically, if you could actually see the particles in the solution, the only thing you're going to see in a solution are methanol molecules and water molecules. You will not see any ions. If you try to pass an electric current through that, won't work. Why? Because there are no mobile ions present, right? And that is basically what is demonstrated in this picture right here. So this is basically the experimental setup to see whether or not a solution will conduct electricity. You have a light bulb here, which is a part of the circuit, which is connected to one electrode, and then the other electrode is connected to the electricity source, and then you flip the switch and nothing happens. The light bulb does not light up, right? So therefore, we call this a solution of what we call a non-electrolyte. A non-electrolyte is basically a substance which, when dissolved in water, does not allow an electric current to pass through, all right? So methanol is said to be a non-electrolyte. But there are two other categories as well. We have what are known as strong electrolytes and weak electrolytes. And strong electrolytes are basically compounds which, when added to water, form ions. And as a result, the ions will allow an electric current to pass through, all right? The key thing you need to remember about strong electrolytes is that the solutes that exist in that solution exist almost exclusively as ions. So basically, relatively speaking, you're going to have a lot of ions present, and because you have a huge number of ions floating around, then electric current can be passed through the solution. And that is what is being shown here in this picture. This is a solution of sodium chloride. Sodium chloride, when you add it to water, undergoes complete dissociation. So you're going to have a lot of sodium and chloride ions present, and therefore, as a result, it will allow an electric current to pass through. And as you can see here, the bulb is lighting brightly because of that, right? Now, you have another group of electrolytes which are known as weak electrolytes. And the difference between weak electrolytes and strong electrolytes is that weak electrolytes undergo what we call partial dissociation, all right? And I think we discussed that in chapter 2, if I'm not mistaken. I think we did the example of acetic acid earlier, but just in case I haven't, basically a partial dissociation is said to be occurring if you start off with a molecule, but it undergoes partial dissociation, which means that only a small fraction of the molecules will undergo that change, right? So the example here is a 1 molar concentration solution of acetic acid. If you look at the picture here, you see that the light bulb lights up, but not as brightly as in the case of the sodium chloride, all right? And the reason why is because the acetic acid is a weak electrolyte, which is made up of mostly acetic acid molecules, right? The concentration of the ions, therefore, in this solution will be relatively low, and therefore it will not conduct electricity as well as sodium chloride, all right? Provided that everything else is the same, including concentration. So basically, those are the three types of electrolytic solutions that we just learned. We have weak electrolytes, strong electrolytes, and then the extreme of non-electrolytes. Okay, what time is it? All right, 40 more minutes. Okay, let's talk about how can we determine the concentration of ions in solution. And this actually is dependent on the stoichiometry of the dissociation of ionic compounds. But before we do that, I want to introduce you to this particular symbol, which you'll be using a whole lot, especially in general chemistry too. The square brackets or parentheses, we use that to represent the molar concentration of what's within the parentheses. So for example, if I were to say, or if I were to write this down, oh shoot, I hate that color. If I were to say or write down this, right? If I were to write on that, the way you should read it is the concentration of hydrochloric acid is 0.50 m, all right? So the square parentheses means concentration of whatever is within the parentheses. That's how you should interpret it, right? Okay, so with that said, let's talk about how do we determine the concentration of ions in a solution of an ionic compound. So let's say you're given a solution of sodium chloride and you're given that the molarity is 0.010 m. So what does that mean in terms of the ions that are present and their concentration? Well, because sodium chloride dissociates according to this equation right here, you can see that for every 1 mole of this that dissociates, the concentration or the moles of sodium ions will be the same, and the moles of chloride ions will be the same because it's a 1-to-1-to-1 relationship. So therefore, we can conclude that the concentration of sodium ions is 0.010, and the concentration of chloride ions would be 0.010. And we can also say that the total concentration of ions in this solution would be the sum of those two, 0.010 m plus 0.010 m, which would be equal to 0.020 m, all right? So that's basically how you can determine the concentration of the ions in a solution containing an ionic compound. You have to pay attention to the dissociation. I think I have another example here. No, I don't, but let me give another example. So let's say instead of sodium chloride, you have potassium phosphate. And this is added to water, and you're going to end up with 3 potassium ions, aqueous, and 1 phosphate ion, right? And let's say that the concentration, where should I put this? Let's say that we're dealing with a 0.010 m K3PO4 solution, all right? So what does that mean? That means that the concentration of potassium ions would be equal to 3 times 0.010 m, which is equal to 0.030 m. And the concentration of the phosphate, PO4 3 minus, would be equal to 0.010 m. And if I were to add the total amount of ions present, that would be equal to 0.040 m. All right? And that's basically how we determine the concentration of the ions based on the concentration of the ionic compound in the aqueous solution. All right, so continuing our discussion of chapter 4, we talked about strong and weak electrolytes. And basically the same principle applies to strong and weak acids, all right? So a weak acid is one that when added to water, only some of the molecules will dissociate, all right? And we saw an example of that earlier in the case of acetic acid, right? Strong acids undergo complete dissociation, all right? And therefore, as a result, strong acids are very good conductors of electricity, while weak acids are not, all right? So basically, weak acids are also weak electrolytes. Strong acids are strong electrolytes, all right? Now, going back to the weak acid discussion, the way we represent the dissociation in terms of an equation is that we use a double arrow to indicate that the reaction goes back and forth. And I think I have that shown here. All right. This is acetic acid. And basically what this is representing is that the reaction goes back and forth. So in the forward direction, the ions are produced, but the ions themselves will recombine to form the original molecule. And again, for those of you who have to do general chemistry too, we'll be dealing with that particular kind of system where you have this back and forth taking place. We call that an equilibrium state, where the rate of the forward reaction is equal to the rate of the reverse reaction. So if you have to do Chem 2, there are at least 3 chapters dealing exclusively with different situations where you have that occurring. All right. Okay. So basically, this is what happens in the case of a weak acid. You have the back and forth, where at the end of everything, when equilibrium is achieved, these concentrations of the ions, the anion and the cation, will be relatively low. All right. And this is just a ball and stick model representation of the same reaction right here. All right. Okay. So that's what happens in the case of weak acids. So this begs the question, how do we recognize strong acids and weak acids? Because some problems you'll be given where it's important for you to make a distinction between those 2 types of acids. Well, typically strong acids are written in their formulas with the hydrogens appearing first, such as these 2 examples right here, but not necessarily so. And again, typically when it comes to weak acids, the hydrogen that is being released is typically written at the end of the formula, right? Again, that's not always the case in textbooks, but, that's, a frequent convention that is used when it comes to representing strong acids and weak acids. However, for our purposes in this course, you guys need to memorize these 6 acids as strong acids, all right? Now, so if you're given a problem with these acids, then you know that you're working with strong acids, all right? Now, I want to make mention, however, of this particular acid right here, which is kind of unique in this list, and that is sulfuric acid, right? You'll notice that in the case of sulfuric acid, you have 2 hydrogens here, right? It turns out that those 2 hydrogens can be lost upon dissociation. So let me show you what happens. In the case of the sulfuric acid, when it dissociates, firstly, it's going to give you H plus HSO4 minus, right? But this anion that is produced here can also behave as an acid. SO4 minus can release another proton or hydrogen ion to form the sulfate ion. All right. Now, here's the thing. Because you have 2 dissociations, what you'll find is that the first dissociation is strong. So I'm just going to put here strong dissociation, or just strong, right? But it turns out that the second dissociation is weak. So I need to put another arrow pointing in the other direction here. And this is a weak dissociation. So that's also very important for you to note, specifically as it relates to sulfuric acid. Sulfuric acid does undergo dissociation, 2 dissociations, stepwise. But the first dissociation is strong, the second dissociation is weak, all right? So you're going to see the importance of that when it comes to certain problems that you will encounter later on. Okay, last thing we're going to talk about here is strong and weak bases. If you understand what we discussed with respect to strong and weak acids, it's the same idea. Typically, strong bases are ionic hydroxides, like sodium hydroxides, potassium hydroxide, and so on. They undergo complete dissociation in water, and therefore will conduct electricity as well. So they're good electrolytes. Weak bases, however, undergo partial dissociation in water, and therefore they are weak electrolytes. And again, we use the same double arrow representation to indicate that dissociation does not go to completion. One common example of a weak base is ammonia, right? And the way ammonia works, let me see if I have it here. I don't have it here. Let me just show you quickly. Ammonia when it reacts with water, forms ammonium and hydroxide ions, right? So again, you'll notice that I use the double arrow here to indicate that the reaction goes back and forth, all right? And ammonia is not the only weak base like that. There are other weak bases that exist, most of them being organic, all right? Okay, and then you need to memorize this list as well as these compounds being strong bases, right? And this one is actually easier to remember because these are all hydroxides of groups 1A and 2A, right? So that's an easier list to remember when it comes to strong bases. If you're given any other base, then basically you can assume that that base is weak unless you're told otherwise, all right? Okay, I think I'm going to stop here. Right, I'm going to stop here. Next topic is neutralization reaction. So a couple of things, make sure that you complete that assignment. Assignment, what is it, 3? Today's what, Thursday? I think I'll make it due next class, all right? So next Tuesday, make sure you have it done. You can turn it into me or you can submit it in Canvas. Remember also your first test. I'm going to, if I get the chance to do it, either today or tomorrow, I'm going to send it over to the testing center. Make sure that you call or not call, go on their website and sign up to schedule a time for your test. The only thing you need to bring is your pen and your calculator. Everything else will be provided, the test paper, scratch paper, and the tables that will be provided as well, all right? And you have until Friday of next week to do it, okay? And I think that's it, yeah. All right, so that's it, folks. See you guys next Tuesday.